The next thing we're going to look at is the derivative of the natural log function. This is stated as a theorem in the book. Theorem 3.13 says that the derivative of the natural log of x is equal to 1 over x. So if we're differentiating the natural log of just x, where x is the argument of the ln, the answer is just simply going to be 1 over x. And this is for x greater than 0. We also have the chain rule version of the same rule. Let's suppose that u is a differentiable function of x. Then the derivative of the ln of u will be it's 1 over the thing on the inside of the natural log. And then you would multiply this by the derivative of the thing on the inside. Typically, I would show this as like 1 over u. And then the derivative of the inside, we can simply call that u prime. Let's take a look at example 2. Here we want y equals the ln of 2x. This problem can be done one of two ways. Let's actually do it both ways. The first way I'm going to do it is by rewriting it using properties of logs. Because we have a product on the inside, we can rewrite this as the ln of 2 plus the ln of x. And now let's go ahead and apply our derivative rules. This piece here, the ln of 2 is a constant. So the derivative of that constant is going to be 0 plus, now this is our standard rule for the derivative of ln. The derivative of ln is going to be just 1 over x. So on one hand, y prime is equal to 1 over x. Alternatively, if we didn't think to do this rewriting step, and if we try to differentiate it as it is, then in this form that would require the use of the chain rule. The derivative of the ln of 2x, according to our rule for logarithm, is it would be 1 over the thing on the inside. So it's going to be 1 over 2x. And now from the chain rule, we multiply by the derivative of the inside function. The derivative of 2x would be 2. That gives us y prime equals 2 over 2x. The 2's simplify, and we get the same answer. We get 1 over x. Let's take a look at part B. We have y equals the ln of x squared plus 1. To do the derivative of this, it's going to be 1 over the inside function. Now multiplying by the chain rule, we need to multiply by the derivative of the inside function. The derivative of x squared plus 1 should be 2x. So y prime is equal to 2x divided by x squared plus 1. Take a look at part C. In part C, what we have actually is a product. We have y equals x times the ln of x. Since we're differentiating a product, we need to use the product rule. Product rule says you do the derivative of the first term. That's going to be 1 times the second term. Plus, now we have the first term times the derivative of the second term. Derivative of the ln of x, that's our new rule. This is going to be 1 over x. So y prime is equal to, we have the ln of x plus x times 1 over x would give us 1. In part D, we have a composition. This is the composition of the cubic function, which is the outermost, and the ln of x is the inside function. Because it's a composition, we need to use the chain rule. We bring the power down, reduce the power by 1, leave the inside function alone, and now we multiply by the derivative of the inside function. The derivative of the ln of x is going to be 1 over x. So we have y prime equals 3 ln of x squared, all divided by x. One of the things that's highly mentioned, and we've talked about this even before we started the calc when we did our review material, is using properties to rewrite things. For example, in number 13, we want to find the derivative of f of x equals the ln of the square root of x plus 1. If we differentiate it in its current form, this is actually going to be a threefold composition. The outermost function is ln. We have a square root function or a 1/2 function on the inside. And then composed with that, we have the polynomial x plus 1. However, if we use properties of logarithms, we can rewrite this. The exponential rule for logarithms, the power rule says you can bring the 1/2 power out in front, and then this becomes the ln of x plus 1. And now we can take the derivative simply by using the constant multiple rule, just leave the 1/2 alone. And then the derivative of the ln of x plus 1 would be 1 over the function on the inside. And then from the chain rule, we multiply by the derivative of x plus 1, which would be 1. So f prime of x is equal to 1 over 2 parentheses x plus 1. And of course, if you wanted to, you could even distribute it through. Entirely up to you. I would probably just leave it factored out. Here's another example, albeit a longer one. Suppose we have this function. It's the ln, where this entire quantity is on the inside, and we want to find the derivative. Okay, this is one where certainly if you don't invoke and use properties of logarithms, the derivative is going to get really messy really quickly. Before we do any calculus, let's take the time to rewrite this thing. According to the properties of logarithms, if we have the ln of a quotient, that's going to be the natural logs of the difference of the two, the difference of the log of the numerator, minus the log of the denominator. That was called the quotient rule for logarithms. To this first term, we now have a log of a product. That's going to be the sum of the logs of the factors. While I'm at it, let me rewrite this square root as a 1/2 power. And now lastly, we can simplify it one more time by using the power rule to bring these exponents out in front as multiples. This is going to be 2 the ln of x squared plus 1 minus 1/2 the ln of 2x cubed minus 1. That's as much as we can expand it and to break it apart. And that's going to make the calculus step much easier. So this step here was all algebra, simply a matter of rewriting it. Now it's in a form that makes the derivative much easier to deal with. We can differentiate term by term. The derivative of the ln of x is 1 over x plus, leave the 2 out in front. The derivative of the ln of x squared plus 1, that's going to be 1 over the thing on the inside. And then from the chain rule, we need to multiply by the derivative of the inside. Derivative of x squared plus 1 is 2x. Leave the constant multiple alone, so we have that minus 1/2 times the derivative of this ln is going to be 1 over the stuff on the inside times the derivative of the inside. The derivative of 2x cubed minus 1, that would be 6x squared. Now let's do a little bit of simplifying. F prime of x is going to be equal to 1 over x plus these two multiplied to give us a 4x over x squared plus 1 minus this 2 and that 6 will make a 3. Half of 6 is 3, so we have a 3x squared all over 2x cubed minus 1, and we'll leave it just like this. So common theme, we've seen it again and again. If you're able to rewrite the function in a way, whether it's using properties of algebra, properties of logarithms, or trigonometric identities, rewrite it first in a way that makes the calculus step much, much easier. The next thing we're going to discuss very briefly is that our derivative rule, so if you go back to theorem 3.13, the derivative, when we define the derivative of the natural log of x as being 1 over x, be very careful here. 1 over x itself is only defined for x is greater than 0. That's the domain of the ln, yet its derivative would actually be defined for values different from 0. Okay, but since this is where the ln is defined, we take its derivative to also be defined on x greater than 0. You can kind of expand this domain and make it a little bit larger if you put an absolute value on the inside. The domain of the absolute value of x would just be all x's that are different from 0. So let's suppose that u is a differentiable function of x such that the absolute value of u is not equal to 0. Then the derivative of the ln of u is equal to u prime divided by u. If you wanted to see a proof of this, maybe I'll do it very quickly. But the ln of the absolute value of u, recall that u is a piecewise defined function. This is going to be the ln of u when u is greater than 0. And it's going to be the ln of negative u when u is less than 0. Therefore, if we look for the derivative, d dx of the ln of the absolute value of u, that's going to be d dx of the ln of u, which would be 1 over u, and then from the chain rule u prime for u greater than 0, and then d dx of the ln of negative u. Pay attention to this step. Remember, the derivative of a natural log is 1 over the thing on the inside, and then from the chain rule, we need to multiply by the derivative of the inside. Well, the derivative of negative u is negative u prime. These negative signs cancel each other out, and we still end up getting the same expression, 1 over u prime, and this one is valid also for when u is less than 0. So what is the derivative of the natural log of the absolute value of u? It's simply going to be 1 over u times u prime. The book makes it a point to put that u prime in the numerator. I feel like this is more to the spirit of the rule, though. The last thing we'll finish this section with is what happens if we have bases other than e. Well, we know that the derivative of e to the x is e to the x. If we have a base other than e, then it's very comparable. The derivative of a to the x is still going to be a to the x, but we also get a multiplication out in front, an extra factor of the ln of a. And then if you look at the chain rule version of this, the derivative of a to the u is going to be a to the u prime, again with that ln of a out in front. If we want to differentiate a log that's different from the ln, the derivative of log base a of x will still be 1 over the thing on the inside, but in addition to that, you're going to have the natural log of the base in the denominator. So it's 1 over the thing on the inside times the natural log of its base. And then example 4 is the same rule, but the chain rule version of it. The derivative of log base a of u is equal to 1 over the thing on the inside times the ln of its base times u prime. Let's take a look at a couple of these derivatives. According to our brand new derivative rule, the derivative of 2 to the x should still be 2 to the x, but also with a multiplication of the ln of its base. Doesn't matter where you put it. I know the book kind of puts it out in front, so maybe I'll do the same thing too. Y prime is the ln of 2 times 2 to the x. Here we have a composition. The inner function when you have an exponential is always the exponent. So we first need to begin by kind of covering this up for a moment. We need the derivative of a 2-power function. Well, we know that that's the ln of 2 times that exponential function back. So times 2 to the 3x. And now from the chain rule, we need to multiply by the derivative of the inner function. The derivative of 3x, which is the exponent, would be just 3. So y prime is 3 ln of 2. That's multiplying to 2x. Let's take a look at part C. We have log base 10 of cosine. The derivative of a logarithm is going to be 1 over the thing on the inside. So it's going to be 1 over the cosine of x. If it was ln, it would just be that, but because we have log base 10, we also need to multiply by an ln of 10 in that denominator. And then from the chain rule, we need to multiply by the derivative of cosine. That's the inner function. The derivative of cosine is negative sine. So y prime is equal to negative sine of x over the ln of 10 cosine of x. And if you like trig and you want to play around with it, you could even get cheeky and do something like, I don't know, negative 1 over the ln of 10 times the tangent of x. Okay. If you want to rewrite it like that. Certainly this, I think, is a little bit easier for a lot of us. It's less work, and it's kind of easier to kind of look back through and match it up using your original derivative rules. But again, especially with a lot of the derivatives that involve trigonometry, you can oftentimes rewrite them. You can find equivalent forms. Unless that equivalent form really helps us at that point in time, there's really no necessary reason to do that. Okay. And then we have one more. Let's take a look at part D. We have another logarithm. Now this is log base 3, but we can use the same thing. Properties of logarithm says we can rewrite this first before we try to take any derivative. This is the quotient rule for logs. It's the log of the numerator minus the log of the denominator. We can then think of this as the 1/2 power and use the power rule to bring that out in front. So we have 1/2 log base 3 minus log base 3 of x plus 5. This is a really efficient and convenient way to rewrite it. So now we're going to kind of go ahead and take the derivative. This is going to be 1/2 constant multiple times a logarithm. Derivative of a log is 1 over the thing on the inside. Because it's log base 3, we also need to have the ln of 3 there as a multiple. And it was just a simple x on the inside, so that's not a chain rule problem. Minus, similarly, we're going to have 1 over the thing on the inside of the log, that's x plus 5, times the ln of 3. And now because there is a composition here, we need to multiply by the derivative of the inside function. The derivative of x plus 5 is simply going to be 1. So here y prime is equal to 1 over 2 ln of 3 times x minus 1 over the ln of 3 times x plus 5.